we've got to find better ways to handle it. We can't throw money at it because the money's not going to be there. So the thought is very strongly that if through research we can have a lot better understanding, stay right at the state of the art, through research we can come up with some innovative ideas, we ought to try them, and we ought to keep abreast of it.
Research into new roadway repair materials and methods by the Strategic Highway Research Program, or SHARP, will help us find better ways to reduce costs and improve pavement repairs. It is estimated that between $18 and $20 billion are spent on roadway maintenance projects annually in the United States alone. Approximately $260 million are spent annually just on pothole patching. SHARP research covers the four most common maintenance activities: pothole repairs, spall repairs, crack sealing, and joint filling and sealing in concrete pavements. SHARP's research goal is to select the best combination of materials and procedures for maintaining a specific pavement that takes into consideration its age, expected rehabilitation schedule, the weather at the time of repair, climatic zone, traffic, and the availability of lane closures. SHARP researchers have chosen sites throughout the U.S. and Canada located in all four long-term pavement performance, or LTPP, climate geographic zones. These tests will continue for several years. It is vital that you do not repair, change, or overlay the test sites in any way unless there is an immediate, serious safety hazard. Altering or covering a test site will destroy its value to the SHARP research project. The goal of this research is to improve productivity by extending the life of repairs, thus decreasing repeat operations, speeding repair times, and reducing lane closures, thus decreasing user delay costs. The end result is that pavement conditions will be improved, making roads safer. Let's review the four kinds of repairs that researchers are testing. In this first part, we'll cover pothole repairs. The objectives of the pothole repair research are to identify optimal materials and procedures for various roadway and weather conditions and compare them with conventional materials, procedures, and equipment. Researchers are testing 8 different cold mix asphalt-based products. 3 general types of repair procedures were used: rapid or throw-and-go repair, an intermediate repair, and a semi-permanent repair. Each was performed under controlled conditions. For the rapid or throw-and-go, repair workers added water to the pothole to simulate adverse conditions. They then placed the test material, overfilling the hole and leaving a crown at the center of the patch, and compacted it with truck tires using a minimum of 4 passes. The intermediate process is the same as the throw and go, except that an edge seal was applied. For the semi-permanent repair, workers removed the loose material using jackhammers or pavement saws. They cleaned and dried the hole using air or a heat lance. They placed the test material, leaving a crown, and finally they compacted with a roller. Although methods varied for each test, the goal for each repair was to provide a uniform, smooth-riding surface. Material testing is also being done in the laboratory. The tests should characterize the properties of a mixture that affect its performance, identify storability and workability of each product's components, and identify structural adequacy of a mix once it is placed in the hole. Final results will not be available until 1993. Analysis will cover 8 failure categories, such as shoving, raveling, and cracking. Are there results yet? Yes. Some failures were noted in early evaluations. These were primarily the local materials. It is believed that these local materials were the first to fail in significant numbers because of their general low-tech production process and the fact that most are stockpiled outdoors for long periods of time. Results also show that the quality of the spray injection material can be highly variable. It seems to depend in part on the experience of the equipment operator and the overall quality of the aggregate. After 3 months, researchers noted only 27 failures of the 860 patches placed, a current success rate of 97%. Divided between local materials and proprietary, the failure rate for local materials is currently at 27%, while the failure rate for proprietary materials is only 1%. Material costs range from $15 per ton to $80 per ton. Cost effectiveness, however, is based on more than just material cost. Key determinants of cost effectiveness are labor and equipment cost, material cost, and the lifespan of the patch. This is best illustrated by looking at results of an earlier study. 2 material types were used: conventional local mix asphalt and a proprietary mix. The proprietary material cost per patch was more than 3 times the price of local mix. Labor cost was the same for each type of patch, a little less than $7. The average lifespan of the local mix asphalt patch was less than 4 months, while the average lifespan of the proprietary asphalt patch was more than a year. This data, along with the placement cost, was used to calculate the equivalent annual cost for each type of patch. As can be seen in this chart, the equivalent annual cost for the proprietary asphalt patch was much lower than that for the local mix patch. The product with the cheapest upfront cost is not always the most cost-effective. A new important element included in the current study is the cost for motorists' time and inconvenience while delayed as repairs are underway. In the second part, we'll cover new spall repair materials and procedures. Spalls often are first found at transverse joints of Portland cement concrete pavement. Spalling is of concern because it contributes to pavement roughness, leading to reduced pavement serviceability and creating safety hazards. Major factors contributing to spalling are infiltration into joints of incompressible materials, mechanical shear caused by slabs deflecting under traffic load, problems during initial construction, including honeycombing, and materials defects. Many different procedures and materials have been tried in the past to correct spalling, with a wide range of results. Permanent repair procedures are time-consuming and expensive. Plus, traffic lanes are closed for a long period of time. Yet, quick repairs with asphalt cold mix usually do not last long, so they must be repeated often. The objective of spall repair research is to determine the most effective spall repair material and procedures for various environmental conditions. The ideal material and placement procedure will be usable in a variety of temperatures and moisture conditions. Require a minimum of patch preparation effort, thereby reducing lane occupancy time of maintenance workers. Provide a long lifespan for the repair. Have a reasonable cost. Not pose an environmental or health hazard to maintenance personnel. And have a short curing time to facilitate early opening of repair lanes and less delay for motorists. Only partial depth patch sites were used. A typical test site was located on a road with two-way traffic counts of between 3,000 and 100,000 vehicles per day. The patch pattern consists of 10 patches. Some patches are forward of, and some are after a joint, and some are on both sides. They are also of varying sizes, with some in the wheel path and some not. There are 11 materials being tested under good environmental conditions, and 3 under adverse conditions. Under good conditions, the materials being tested included 2 asphaltic, 5 cementitious, and 4 polymerics. For adverse conditions, both cold and wet, 3 materials were tested: 1 asphaltic, 1 cementitious, and 1 polymeric. Along with different materials, researchers tested a variety of different patching procedures, ranging from rigorous to simple. Procedures included concrete removal by saw cutting and jackhammering, hand tools, milling, water blasting, and by jackhammering and sweeping clean. To simulate adverse conditions, water was then added to the spall hole. Laboratory tests are also being done for spall repair materials. These tests will help highway agencies compare new innovative products to the existing standards in the lab prior to field trials. Possible failure categories include spalling, cracking, wearing or raveling of the surface, bond failure, and adjacent patch deterioration. Once again, there are some early results. Fewer than 2% of the installed patches have failed. However, some cementitious products have developed hairline shrinkage cracks in large patches. Type 3 cement with accelerators can provide rapid setting repairs at costs lower than those of proprietary materials. In the end, we will answer questions such as, are quicker, less labor-intensive methods possible with these innovative materials? Which products have the shortest curing time? And which products or procedures are the most cost-effective considering upfront costs, reduced delay costs for the motoring public, and life expectancy? In analyzing cost-effectiveness, materials experts continually stress that selection of products should not be made on price alone. Sometimes the most expensive material also works the best. Selecting the cheapest product may, in the long run, be the most expensive choice. It is important to remember that because of the long lifespan of the materials, you must take special care not to overlay or in any way alter the test sites. The final two kinds of repairs that we'll cover are crack and joint sealing. Poorly sealed joints can cause problems such as faulting, spalling, and blow-ups. Unsealed cracks also contribute to pavement failure. Sharp research is identifying cost-effective materials and procedures that reduce the amount of water that can enter a pavement structure through joints and cracks and prevent intrusion of incompressibles. Research includes field tests and lab analysis. The lab tests are correlated with field performance. In this way, future innovative materials can be analyzed in the lab to determine if they are acceptable replacements for other products. Researchers are testing two types of materials: sealing materials and filling materials. Each of the materials were tested under a variety of configurations and preparation methods, including plowing, routing, sandblasting, backer rods, and Band-Aids. Once again, final results won't be available for several years, but to date, there are clear observations we can make regarding installation. Some products require very controlled heating and placement procedures, thus making them difficult to use. When cleaning cracks, debris must be blown off the road so that it will not contaminate the new seal. A 1/4-inch recess is necessary with silicone seals so that traffic will not pull the material out of the crack. A heat lance used on wet cracks works well as long as the surrounding base is not saturated with water. Silicone sealants are easier to install as they require no heating. We can also make some early performance observations. Asphalt Band-Aids used in this research showed early wear from traffic. Virtually none of the concrete joint seals have failed. Silicone sealants work well if the backer rod is installed properly and the sealant is kept clean prior to setting. Self-leveling silicone sealants are easier to install. All silicones are exhibiting excellent adhesion characteristics and outstanding resistance to intrusion. Backer rods are vital. They serve the dual role of providing a bond breaker at the base of the reservoir and support for the sealant material during setting. Early results indicate that sealant construction-related failures are caused by 1. The presence of dirt, dust, old material, and moisture prior to sealing. 2. Loosened aggregate or pavement fragments not removed by cleaning operations. And 3, leftover material, such as old asphalt sealant, remaining in a joint sealed with new silicone. Sharp researchers are finding better ways to make cost-effective pavement repairs. It's clear that a great deal of careful preparation, study, and installation effort has gone into this testing. Although the Sharp program will be complete by 1993, research into cost-effective pavement repair will continue with the long-term pavement performance program for several more years. Because of the long time span and the value of this research, one critical point must be stressed. Preserve the test sections. They're marked by signs. If near-term road repairs are necessary in test areas, follow these simple procedures. Do not repair, change, or overlay the test sites unless there is an immediate, serious safety hazard. For situations other than an emergency, call Sharp or FHWA at the number on the screen. If you would like more information about this research project, call Sharp.